Okay, now let's pick up from the last video. We left off with this bullet right here. It says, what happens to your graph if the probability of success is 50%, greater than 50%, less than 50%? Let's look at our graph. Now, it's still in the cumulative mode, so we're going to change that back to non-cumulative. So let's change this from a 1, making it true, to a 0, making it false, and then put it back in non-continuous framework. So this is our original distribution. The change we need to make next is to convert the probability to 50%. So instead of 20%, we're going to put 0.5 and then drag this down. Now you will notice that it makes it a symmetrical distribution. In other words, the probability of getting a low number of people that are colorblind is the same as the probability of getting a high number. You have a 1.6% chance of getting 0 people in your sample that are colorblind, and you have a 1.6% chance of getting 6 people in your sample that are colorblind. And then same thing, the probability for 1 and 5 are 9.4, probability for 2 and 4, 23.4, and then the probability of 3 is 31%. So it's a symmetrical bell-shaped distribution. Now what happens if we change this to a number less than 50%? Well, we already had one. It was 20%, so we could just go back to that one and look at how it's different. And you'll notice we get a right skew, meaning that you have a low probability of getting someone that's colorblind, so clearly you're going to get few people that are colorblind. Zeros, ones, and twos are going to be common. And then the larger numbers are going to be less common. So you get this right skew. Okay? And what if we change it to something higher than 50%? Okay? Let's take it to 80%, 0.8. And watch what happens here. Now we get a left skew. If there's an 80% probability of getting people that are colorblind, you're going to have very few zeros, ones, and twos. You're going to have a lot of, 5s, 4, 5s, and 6s. So there is an intuition behind this. Okay, now let's do the next one. It says, is the binomial distribution the appropriate model to use in answering this question? To answer this, we need to go back to the requirements for the binomial distribution and make sure that it meets all of them. First, are there 2 outcomes, success and failure? Yes. Is either colorblind or not colorblind. Are there a fixed number n of identical trials? Yes. We selected 6 people in our sample, so n equals 6. Stationary probability. Yes, we established that the probability was a constant 20%. And independent trials. To ensure this, we either needed to take the sample with replacement or from a very large population. Since we selected 6 people from the larger population, we would expect independent trials. So the answer is yes, this is an appropriate model to use to answer the question. Let's move on to the next one. It says 40% of a school's population is female and the entire school has 30 students. You randomly select 10 students to attend a lecture on industrial statistics. Using Excel, create a probability distribution table and graph. So very similar to what we did in the first example. We're going to create in our column here the possible outcomes. And since we selected 10 students, there could be 0, 1, 2, 3, all the way up to 10 females selected. So that's our first column, 0 to 10. Then in the next column, we put the binomial function. And we've got to set this up. So we know the number of successes is going to be our first column. For trials, there's 10. The probability of a success is 40, so 0.4. And we don't want a cumulative distribution at this point, so we're going to put 0 for false. Okay. And again, I like to use percentages we can round to the 10th place and then pull it down. So this is our discrete probability distribution. Next, it says create a graph. So we're just going to scroll over our data here, insert, charts, column, select the one, vertical one, and then get rid of the unnecessary bars, get rid of the redundancies. Again, we run into this problem with 1 being the lowest number, so we're going to go up here to select data, and for our horizontal axis, we're going to select the first column, and that should fix it. And it does. Okay. Check it just to make sure. Pick any bar, 12.1% for 2, and it looks like 12.1% for 2. Okay, so it looks good. Next, it says, based on the results, what is the probability that exactly 6 of them will be female? Well, we can look at our bar, and it's 11.1, or we can look at our table, 11.1. What is the probability that more than 6 are female? Well, there's a couple ways to do this. One way is to add up the probabilities for each value that is greater than 6. Put equals here, the probability of 7 plus the probability of 8 plus the probability of 9 plus the probability of 10, and you get 5.5. The other method would be to convert this into a cumulative distribution and then just subtract the cumulative value up to 6 from 100%. For example, if I go up here, I can change this from 0 cumulative to 1, making it true, and then scroll down. Now I have a cumulative distribution. I know that each one of these numbers tells me the probability of getting a value up through that point. So the probability of getting a value of 0, 1, 2, 3, 4, 5, or 6 is 94.5%. Therefore, if I subtract that number from 100%, I get the probability of getting a value 7, 8, 9, or 10. And notice it's 5.5, right? 100% minus 94.5% is 5.5. So 2 routes to the same end. Okay, next it says, is the binomial distribution the appropriate model to use in answering this question? To answer this, we need to go back to our requirements. 2 outcomes, success or failure. Yes, because you either have female or you don't have female. Fixed number of n identical trials. Yes, we had 10 trials. Stationary probability. Yes, it was 40%. Independent trials. For this, we either need to take our sample with replacement or from a very large population. This requirement is not satisfied. Go back to the question and note that because we selected 10 students from a school of 30 students, we are not selecting from a large population, meaning that the binomial will not work optimally to evaluate the probabilities of this scenario. Instead, we would use a different tool, which is called the hypergeometric, and we'll get to that later. Now let's move on to the second discrete probability distribution called the Poisson. This one is used when successes can be defined across an interval of time or distance, as opposed to a fixed percent that defined a success in the binomial. Example might be the number of potholes per mile of road. That would be an interval of distance, or emergency room patients per hour, interval of time. It's often used in place of the binomial when success can be determined but failure cannot. If you're studying traffic accidents, for example, you might run across data that shows you the number of traffic accidents last year. Well, that would be success across time. Or you might find data that shows the number of traffic accidents per 100,000 miles driven. That would be success across distance. In both instances, however, you can't define failure. Contrast that with data that tells us the percentage of Americans that have been in a traffic accident. If it's 60%, then that means 40% have not. We can define success and failure. So based on the data that you're using, the binomial may be appropriate to study probabilities, or the Poisson. The next three requirements for the Poisson are similar to the requirements that we saw for the binomial. The distinction is going to be that with the Poisson, we're dealing with intervals, whereas with the binomial, we were dealing with trials. Regardless, the number of successes per interval needs to be identifiable. You have to determine how many patients are showing up at the emergency room per hour, how many potholes there are per mile, etc. There needs to be stationary, constant probability. It can't change from one interval to the next. The probability of an emergency room visit needs to be the same for the first hour, for the second hour, for the 5th, 10th, so on and so forth. The probability of potholes per mile occurring needs to be the same regardless of the miles that are being analyzed. And then finally, independent intervals. What happens in one interval should have no influence on the probability of subsequent intervals. If there are a large number of potholes in one particular mile, that shouldn't change the probability of potholes in the subsequent miles. Assuming all of these criteria are met, we can then use the Poisson to do our analysis. Let's now shift over to the next slide and do some manual operations. First, with the Poisson formula, and then we'll move into Excel. So this question here says, a college switchboard gets an average of 3.5 crank calls per day. Find the probability of 2 such calls in a day. Clearly a Poisson problem, because we're defining successes across time. Using this formula, we'll replicate it down here. We want to find the probability of 2 calls, and that's going to be equal to, in our numerator, we put the mean, and that's given to us. The mean is the average, so we put 3.5, and we're going to take that to an exponent of x. Well, x is the number of occurrences in an interval. So x in this case is going to be 2. And we're going to multiply that by base e to the negative mean. So we'll just keep e there and put negative 3.5. And then we're going to divide that whole thing by 2 factorial, okay? Because again, x is 2. If you run the numbers in Excel, and again, we're just going to use Excel to do the computations, you will get the following. Let's do our numerator first. 3.5 to the exponent of 2. And I'll just put that one there. Then we're going to use the exponent function. This is a specific function in Excel, which if I pull up the argument menu, says returns e raised to the power of a given number. So we're going to raise it to 3.5, right? Just like we saw here, e to the negative 3.5. Now we have these two values. We can multiply them by each other to get our numerator. So that is our numerator. And then we're going to take that, we're going to divide it by 2 factorial, which we know in our head, but let's use the function. Remember, Excel has a factorial function. And we're going to put 2, that. And if you do that correctly, you get 0.1849. Finally, let's go ahead and calculate the mean and the standard deviation. The mean's easy. It's given to us. No calculation involved. 3.5 crank calls. The standard deviation is going to be the square root of the mean. We can do that right here. Put equals, use Excel's square root function, and we want to put 3.5. That's our mean, and then we can find out that that is 1.87. All right, that's it.